Hello, everybody, and welcome to the Differential Drive for Gazebo Simulation webinar. I am Ricardo Téllez. I'm one of the creators of the Construct, and today I'm going to show you how you can build a basic differential drive for Gazebo. As you know, this is one of the most common things that you will do when you are trying to simulate robots. So it's very important that you master how to do that. For this webinar, we are going to use a zip file that contains the structure of the files that a simulation must have in order to be able to be launched, including ROS controllers. You have received this file with your subscription to this webinar, but in case that you have not, you can follow our post that describes how to do a differential drive for Gazebo that is posted here, as you can see, in our webpage. You can just go to theconstructscene.com, and then there you will find a complete description of what this webinar is about. You will also find a place where to download the zip file that we are going to use in this webinar. As I told you, when you subscribe to the webinar, this is going to be a very practical webinar. So we are going to do at the same time that we are learning how to do it. So it's important that you have downloaded this zip file, and it's also important that you have a free account into the Construct. That is, as you probably know, it's a place where you can launch simulators in the cloud. So it's not mandatory. If you don't have the Construct account, it's okay. You can do it, the same things, you can do them in your own Gazebo simulator, in your own computer. But I really recommend you that you take a free account of the Construct, because it's easier, it has a lot of advantages, and it's just an opportunity for you to test how it works and how convenient it is for you and for your simulations. So just visit our website and you will be able to get a free account. So let's start with how to do it. Okay, the first thing is that we are going to log in into the Construct. So I have already logged with my name, my username here, and this is the main page. In case that you are not using the Construct, you can just prepare your Gazebo simulator. Now we are going to launch one of the simulators. So here we go to simulator, we reach this place, and today we are going to work with Gazebo 4, but the same thing will work for Gazebo 1.9 or even DRC simulator. So today, Gazebo 4 with ROS Indigo. So we just run the simulator and we go. In the meantime that the simulator is booting, we are going to upload to the Construct the zip file that I provide you. So I go here once and upload a wall. I will select from my computer the zip file. So the zip file must not be uncompressed. So it has to be still a zip file. So just as a zip file, I just select and click, drag and drop, and then say upload. Everything went okay, and now I have here my differential drive zip file uploaded. Let's return to the simulation and see how it goes. Okay, this is still booting and doing thing. So in the meantime, let me take the opportunity to tell you that you can ask questions. We'll have 10 minutes of questions at the end of the webinar. You can just write them down in the panel that is on the right-hand side of this broadcast. So just write the questions there and they will reach me, and I will try to answer as many as possible by the end of this webinar. Okay. What else? So yeah, so what we are going to do is just We have a simulator that is ready for us. Now it has started. It has finished booting. Now it's going to appear here, the main screen of the simulator. Here it is. And now we are ready to start building something on this simulator. For this, we are going to launch the zip file that we just have uploaded. So I'm going to select worlds and launch a world. Here, there is a list of all the worlds that I have uploaded into the construct. I have several. Here, my worlds, also the default Gazebo worlds. But I'm going to select the differential drive that I just uploaded. Run selected world, and that's it. So I am launching this differential drive into the empty Gazebo simulator. For the people that is not using the construct, you can just do the same by just uncompressing the differential drive zip file. You must uncompress those packages into a place that is included into the ROS package path of your system. So if you compress that file, you will see that there are two different directories, and you will be able to interact with ROS launch with those files. Okay, so yeah, so here is the zip file that the differential drive will. It's empty, of course, because we have to build our robot yet. But now it has been loaded into the Gazebo simulator. Because of that, I am able to use the editor that we have embedded here to see the files into that world. So let's have a look at the world. So it looks like you cannot see the editor. It's not being shared here for you. Let me check what is happening. Let me check this. Maybe I will have to share more things. Yes, share. Okay, so now you can see the editor. So this is what the zip file contains, all those files. Okay, this is a mistake of mine. I included some macOS files, but we can just delete them in order to prevent mistakes. And so, yeah, so this is the structure of a world, of a simulation, following the structure that Gazebo has defined by themselves. So if you want to create a complex simulation in Gazebo, it is recommended that you follow this kind of a structure. First, you have to create a directory that is called your robot underscore description, and you must include some files in there. Then you have to create another one that is called your robot underscore Gazebo, and also include some files. For the complete specification of the files inside there, you must visit the Gazebo web page that you will see. But now we are going to concentrate only on this file because it's the one that interests us for the differential drive. For the differential drive, we have a launch directory and a models directory. Here inside the models is where we are going to include our model of a differential drive robot. You can see that you already have some files that I have put for you, but they are empty. So if I try to open this one, you'll see it's empty, and this one is also empty. Our exercise today is to learn how to fill those files and see what the results are inside the construct. So now what we are doing is to creating a model of a differential drive. For that, the best place is to put it here in the models directory and call it differential drive. Then build those two files, model config and model SDF. There are some other files that you can include also inside the model, but we are going not to talk about it today. So the first thing is model.config. This file, it contains just a description of what your model is going to be, who has done, when, how to contact the author, etc. So it's just a description of data that is related to the model. In order to write down the model.config file, here you can just copy the code that is included into the blog post that I showed you at the beginning. Still, you cannot see it. So let me. So here, yes, we have the code for the model.config. Here it is, model.config file here, and here we have the text that we should put in there. So I'm just going to select and copy and select. Okay, up to here, copy and put it back. And again, you cannot see. Okay. Yeah, so I have copy and pasted it here. I will put my name here and address, whatever, email, and it's a simple differential robot with ROS. Okay, that's good enough. Just pay attention to the name that you are putting here. This is very important. Has to be the same as the name of the directory there, and it's going to be used to refer to this model. So the name that you put here, when you include this model in other simulations, you will have to write exactly the name that appears here. We call it differential drive. Okay, now so we have this, we can just Control S to save this file, and we have modified the model config file for the differential drive. And now we are going to populate the model SDF file. The model SDF file is the main file. This is the one that contains the description of your robot. So it will describe how big it is, which shape it has, which kind of joints does it have, the mass, etc. In this case, what we are going to do is just a very simple differential drive that contains a base, we'll call the chassis. Then it contains two wheels side by side, that's the differential drive. And it also contains a caster on the front in order to prevent the robot to fall. It's a caster is just a wheel that is not actuated, doesn't contain a motor. Okay, so for the same thing, we are going to populate this file following the text that is in the blog post. So I'm going to return to this blog post, and the same problem here in the Hangout of sharing the screen. Here it is, here we are. And so this is for the config file, and now for the model SDF file. So this is going to be the basic structure of the file, and I am copying it. And pasting into the editor in the model SDF file. Okay, so now we are going to add the chassis. The chassis is the base. Is the base, so is what is going to constitute the base of the robot to the part to which we are going to attach the wheels and the caster. And for this, so I just keep on copying then this following text that is here. and I'm going to copy, and afterwards I'm going to explain you what it says. Copy and then paste into the editor, but you cannot see. Okay, now. So this is the basic structure of the model SDF, and now we are going to add each one of the parts of the robot as a link. Each part of the robot, it's defined as a link, and the base is also another link. And the text that I have copied from the blog post contains the links, the link data describing the chassis. As you can see, link and chassis. It also contains some other parameters like the pose. This means where I'm going to put it into the wall. And also the mass and the inertia. Okay, about the inertia parameters, so this is a little bit tricky, and we are not going to talk about that here today because it takes a lot of time. But you can follow a link that we have included into the blog post if you want to learn how to do it. Just take it for granted now for this example. Every link like the chassis, it's divided into two parts. First part is the collision, and the second part is the visual here. The collision defines the geometry of the chassis in this case. So it's the geometry of the link that you are describing. In this case is the chassis. So it defines the geometry in terms of physics interactions. So this means that the simulator will use what you put here in the geometry as the thing to compute how your chassis collides against other objects and how it interacts with other objects. In this case, we are going to create the chassis with the shape of a box of this size. So it's very simple. This box is the one that is going to be taken into account for collisions. But then, on top of that, you can define the visual. And the visual is the visual representation of the chassis in the simulator. It's just a matter of how it looks into the simulator. So it doesn't matter how you represent it, because it's just for looking when you are creating your robots and then you want to see how they look. So you can define this look here in the visual. In this case, we have selected the same kind of structure for the visual, but just a box. But you could have put anything. Yes, instead of a box, you could put a sphere, for example, or your own mesh describing the shape, a very strange shape of a robot. And then on your simulator, it will appear this shape, and you will see your robot as having that shape. But actually, when it collides with other elements of the simulation, it will be just the box here in the collision that will collide, not the shape that you have defined in the visual. Okay, in this case, in order to simplify, we have put the same visual for the chassis. Good. So now we have this link here. That is the link of the chassis. Now, we are going to add the caster wheel. For the caster wheel, you go again back into the blog post, this here, and capture the code that describes the caster wheel. Now here is for the caster wheel, and it's basically the same. So we have to have a visual for the caster wheel and a collision for the caster wheel. I have a problem here selecting. Here it is. Copying and then pasting. So in theory, this link should be included after the link of the caster, but of the chassis. But the thing is that caster, it's a part itself of the chassis. We want it this way. Because of that, we have to include the caster definition inside the same link of the chassis. Here it is. So yeah, collision, caster collision, and here the visual for the caster visual. Basically, we have created the caster as a sphere, just a sphere of 0.05 meters. And the visual is also exactly the same. Okay, one thing that we have included here in the caster collision are all those parameters for the surface and the friction. Those parameters describe how this sphere is going to interact with other elements, like, for example, the floor. Because we cannot generate in Gazebo a caster that rotates in all the directions, because it's not supported. The way of creating a caster here is just by adding a sphere that has very, very low friction values, I mean 0 values. Then actually the sphere is not rotating when moving the robot around, but just sleeping. And that's the trick. So this is specified in those parameters here. So now we have the chassis and a caster attached to it. Now it is time that we add 2 wheels, one on the left and another on the right. For that, again, we go back to the blog post. And select the code that describes the differential wheels. So this is the code for the left wheel. And also below is the code for the right wheel. So I'm going to copy and paste both of them. Each wheel is taken as a separated link from the chassis. So we have to create a different link for each wheel. So I have copied here and pasted the left wheel. It's a different link after the chassis link. The chassis link ended here. Now this is the left link, and now I'm going to paste. Yeah, the right wheel is here. Okay. So far so good. So we have a chassis that is described here. Chassis link with its collision and visual. Now we have also a caster in front of it. This is the pose where we put the caster inside the chassis. And then afterwards, we have another link with the left wheel and another link with the right wheel. Each one has its own pose related to the center of the chassis. Okay. So if we save this now and we launch the simulation, then we will see the results up to here. Okay, we should see the robot with the chassis, the caster, and the two wheels, but still won't be able to move. We'll reach that point later. Okay, so yes, I have saved it, Control S. If you are using Gazebo, normal Gazebo, just save it also, and do a ROS launch, differential drive, main.launch in order to launch your current state of the simulation. For the construct, for the people that is using the construct, is easier. We just go to the construct. Let me just share again. We just go to the construct, and here we just have to do the relaunch. So this button here will relaunch the current loaded wall. As you remember at the beginning of the session, we loaded the differential drive wall, but there was nothing because it was empty, still to be done. And now we can just reload the wall and see, okay, how it appears here, the robot. You can see it's very simple, but it's what we wanted. So this is the box, the caster wheel is here beneath, and the two wheels. Okay, so far so good, it's working. Now for more interesting part, that is adding some control to the wheels so we can move the robot. For this, again, we need to go to the post and add some stuff. First, we have to say, to indicate to the simulation that the two wheels that are two different links of the simulation, they are attached to the chassis by a joint, a revolute joint. That means a joint that rotates. So this is exactly the code that is included here, and that we are going to include just right now. So I'm copying it. This is for one wheel and for the other one. And you cannot see again. So at the end of everything, we are going to include that code. This kind of code, what it indicates, it's a joint that is of the type revolute, and we call like this, whatever. We are going to put this joint at this position with related to the child, that is the left wheel, that connects to the chassis, and that rotates in the y-axis. The same is done for another revolute that connects the right wheel with the chassis. So it's exactly the same. So now we have indicated that those two wheels that are side by side to the chassis, they are connected through a revolution. So that can spin, can turn. Now, the last step is to indicate who is going to control those joints, who is going to make them turn. And if we go back to the post, you will see that this is made by a plugin. The plugins, you can create many different types of plugins in ROS, but in this case, we are going to take a differential drive controller. And this is the one that is going to control both wheels as by means of ROS topics. So the plugin name is this one, and the file that provides this plugin is this one here. So you just have to copy and paste this code into the editor. Here. And just let me show you a little bit about the plugin. So apart from the name and also which file is providing the code that has to be executed, this plugin has some parameters that are here, all those parameters. It says the left joint, which link is taking charge of that, and the right joint exactly the same. And well, the separation, you need to specify the separation between the wheels and the wheel diameter, how much torque those joints should be able to do. And also, this is very important, this is the topic on which this plugin is going to accept ROS commands. So basically, those are the most important parameters. So now with this code, we have our model completely done, and we can then save and relaunch the wall again. This time, we are not going to see many differences visually, because we haven't changed visually the model, but we have added the control part. So we'll be able to send commands. So I'm going to reload the current wall. And here it is. Okay, so here we have our robot. And now it is time that we try to see if it really the controllers can manage this robot or not. For this case, we are going to use another tool inside the construct, that is the web shell here. If you are using Gazebo, then you can just use a normal shell in order to launch the following command. So let's open this web shell. And because it's difficult to share both things here in using this Hangout, both the screens, I'm going to share with you the whole screen. I think that would be easier, yeah. So let me show you the entire screen. Okay, so yes, now you are seeing everything that is here on my screen. And so this is the shell. I'm going to close it and then just launch it again in order to see. So we are here on the simulation, and I'm going to open the shell. This is a shell that is directly attached to the computer that is running this simulation here. So because we are running a plugin that accepts ROS commands, we can just type ROS topic list in order to observe how many topics are being published by our controller and by the simulation. And as you can see, there are some topics here. And the most interesting one is this one, the common bell. As I told you before, this is the topic that this robot is publishing. This robot is publishing in order to accept robot commands. We can control this in a very simple way by just typing the ROS topic pop command into the command bell. And then, sorry, it was, the type of message was, okay, don't remember the type of message, but we can just find it in a ROS topic info of command bell. And we'll see that is a geometry message twist. Okay, so this is the message, the type of message that this command bell is accepting for velocity commands. So now let's go into publish. on this topic. Command bell, a message. Sorry. Well, a message containing the speed. It's not accepting this. Okay, let's see. Okay, so yeah, I don't know which key I have. Press. Okay. Okay, looks like it doesn't want me to paste this data. So I'm going to type it directly. Geometry message paste. Now, if we double tap after having written geometry message twist, the will autocomplete the message. I only have to change this value of x in order to specify the speed that we want the robot to move. I'm going to put 0.1, for example, and we'll see the robot move. Okay, until we press Ctrl Z, pressing Ctrl C, and should stop. Oh, Ctrl C now. Okay, so yeah, you see, we can move the robot using the controllers that we have included. Oh, it should have stopped. Should have stopped. Okay. Now, we are going to control the robot instead of with one topic with the keyboard. For that, I have included into the zip file that you have launched here, a special launch file that will allow you to control this robot through the command bell topic using your keyboard, the keyboard of your computer. So if you type ROS launch differential drive, Gazebo, and then keyboard, Telep launch it. Now you are ready using the keys that are specified here. You are ready to move the robot. So yeah, if we press the keys, we are moving the robot. So I'm pressing the keyboard now to move the robot. I can make it turn also. One side, the other side, stop, move backwards, move forward. Just pressing the keys as described here. And this is is the end of the webinar. I have shown you how to how to build a robot, a basic differential drive robot, how to attach some joints into this robot, make them revolute by using a plugin that accepts ROS commands. I have also included here some files that you can use as a template for your own project, like the Model 1 or this keyboard launch that will allow you to move very easily and test very easily your robots in the simulations for the robots that you built. And now, so this is the end of the webinar. In case that you have any questions, I'll be happy to hear them here in the channel. So yeah, waiting for your questions. I'm going to stop here and just go back to the how to build. So I don't know if there is a problem with this questionnaire, but I'm not receiving any question. And in case that there is some error, some mistake of this, that could be because it has been behaving a little bit strange. So please feel free to send me your questions through email. You know our emails for contact. For example, if you want to contact me directly, is rtellez, TELLEZ, at theconstructsim.com. I will be happy to answer your questions. Or if you want in general to any member of the team, you can send us just to feedback at theconstructsim.com. So I'm waiting here for some seconds more to see if any of the questions appear, but it looks like it's not. And so we are going to close this today, and thank you for coming. And I hope that I will see you again in the next webinars. Thank you.